Okay, I think we can start now. So let me introduce today's speaker. So today we have Dr. Ilya Belopolski from Princeton University. So Ilya got his undergraduate degree from Columbia University in 2012, major in physics. And after that, he joined at Princeton University as a graduate student. And he graduated in 2019, last year. So he actually worked on various phases of topological quantum matter. So he is one of the driving force of all the discovery of this magnetic topological phases like magnetic Weyl, magnetic Dirac material, and so on. So he publishes many papers in Nature and Science. So in today's talk, he's going to talk about two of his recent compound. So those are basically the topological Weyl loop. So this cobalt-based ternary compound. And Ilya is soon going to be join Tokura Group of Japan as a special research fellow. So with that, so let me welcome Dr. Belopolski. Ilya, take it away.
Okay, great. Yeah, thank you, Madhav. Thank you for for inviting me and for the nice introduction. So first, I hope everyone is safe and in good health. Um, and today we had some problems with the internet at my house, so I apologize in advance if there are any issues with the connection. So yeah, I'm very excited to share our recent work on these two magnetic materials, CO2 MnGa and CO3 SN2S2. So I'll try to convince you that we've observed topological Weyl loops in these materials. So these, one second, sorry. So these projects are the results of a collaboration between approximately 4 groups. So let me first thank the really talented staff scientists at the synchrotron ARPAS beamlines, where we carried out the ARPAS measurements, specifically at SSRL in California and at the Diamond Light Source in the UK. And Claudia Felser's group provided the samples. We also had support from Xin Lin's group and Titus Neupert's group for first principles calculation. And of course, I acknowledge all of my group mates who I worked with very closely on these projects. Let me just highlight Guo Qing, who performed the first principles calculations for CO2 MnGa. And also I worked closely on the ARPAS for CO3 SN2S2 with Tyler Cochran, who's a younger student in our group. And of course also acknowledge Zahid. So let me start by saying a few words about topology broadly. And please, of course, interrupt at any time to ask questions. So a key concept in topology is the bulk boundary correspondence. So it's the idea that there's some interesting relationship between the behavior of electrons in the bulk of a sample and on its surface. So I have in mind a half-infinite crystal. So when we talk about surface states or surface electrons, I'm thinking about electrons whose wave functions are primarily localized in the top few atomic layers of the sample. And then the sample sort of extends down to infinity. And when we talk about bulk states, we're thinking about wave functions that are sort of delocalized throughout the entire sample. And so for topological phases of matter, the situation often looks something like this. We have some exotic emergent quasiparticles in the bulk. These are associated with some topological invariants. And the topological invariants tell us something about the way that electrons on the surface must behave. So there's some constraints on the nature of the surface states due to the topological invariance. And the converse is also true, that by studying the surface states, you can calculate or measure the topological invariance in the bulk. So let's look at some examples of topological invariance. So here are two, the Chern number and the Berry phase. Psi here is the single particle wave function of the electron. And, okay, so this is some, complicated math. But there are two kind of properties that, I'd like to highlight. So the first is that we have some integral here. So in some sense, this quantity is global. We're sort of incorporating the information from many electronic states. And the second is that the values are restricted. So in the case of the Chern number, it can only take on integer values. In the case of the Berry phase, in the cases of interest, it can only take on values of 0 or pi. So these two properties, the fact that it's global and that the values are restricted, this already points to a connection with mathematical topology. Topologists are often interested in characterizing the genus of surfaces. So, for example, how many holes are there in the donut? So here's, here's your Boston cream, which has no holes, so genus 0. Here's your kind of typical American donut, which has 1 hole, genus 1. And then here's an interesting pretzel, which has 2 holes, genus 2. And so you can see that this genus shares some properties with the Chern number and Berry phase. So first, this global nature that you have to sort of inspect the whole donut in order to get the right genus. And the second is that the value of the genus is restricted. The number of holes in the donut has to be a non-negative integer. And so that sort of relates to the restricted values for the Chern number and the Berry phase. Yeah, any questions? Okay. So the big picture in our field is, as I'm sure many of you know, so we're interested in questions like what are the topological phases that exist? Can we write down new topological invariants? Can we find actual crystals that exhibit these topological invariants? And what are some of the unusual transport optics or other properties that could arise in these materials? And so in this talk, I'll predominantly focus on two. So I'll argue that we found two materials, these two magnetic materials, which exhibit this Weyl loop topological phase. And so in a sense, you can understand this talk as being similar to this interesting news article that I saw recently, the donuts with 3 holes invented. So yeah. So the technique that I'll be mostly using is angle resolved photoemission spectroscopy. This is essentially a glorified photoelectric effect, which goes back to Hertz in 1887. And if you start with a photoelectric effect and you work very, very hard and spend a lot of money for 130 years, then you will arrive at something that looks like this. And this is sort of a modern ARPA's setup. So what are the essential components here? Well, we have a light source. Here it's a laser, but in the case of the data that I'll show, it's synchrotron radiation. And then this laser is incident, the light source is incident on a sample. So in our experiments, we're typically working with samples that are maybe 1 millimeter cubed in size. We put the sample into ultra high vacuum conditions. We cleave it under UHV to produce an atomically smooth surface. And then as far as then the light source shines on the sample, and the state-of-the-art synchrotron ARPA spot size nowadays are about 10 micron by 10 micron. So that's sort of a very good spot size for us. And then the light source will emit, will cause some photoelectrons to be emitted from the sample. And these will, of course, sort of fly off in all directions. Some of them will make it into the electron analyzer, which can measure the kinetic energy of the photoelectrons and their angle of deflection, or the angle with which they're emitted from the sample. So then we can use rather straightforward energy and momentum conservation to calculate what the energy and momentum of the electrons were in the crystal. So for example, here we have h nu. This is the energy of the light. This is the work function, which we can determine. This is the kinetic energy, which we measure with the electron analyzer. And then together, these quantities allow us to calculate the binding energy of the electron in the crystal. Similarly, we can calculate the momentum. So we sort of have two angles that we focus on. We have this theta angle, which is kind of the emission angle of the electron in the plane, left or right, and then gamma, which is the emission angle up and down. And you can sort of see that, okay, at small angles, you essentially have kx being proportional to theta, ky being proportional to gamma. And this last component, what will be useful to know later about this component is that it's closely related to the photon energy. So we sort of calculate the out of plane momentum component of the electrons, through energy momentum conservation. To probe different kz in our experiments, we change the photon energy. So we'll have measurements where we change the energy of the incident synchrotron radiation, and then we'll use that to map out the kz direction. By changing the experimental parameters, we can be more or less sensitive to the bulk states or the surface states. And so this naturally already points to exploring the topological bulk boundary correspondence that I just introduced using ARPAs. So before I introduce Weyl loops, let me sort of set the stage by talking about some of the quasi-particles that are familiar to us from topological phases we've studied before. So here is an ARPA spectrum of cadmium arsenide. This was work that was led by Madhab, one of the first projects that I was involved in when Madhab was in our group at Princeton. And what you notice here is this linear dispersion of the electronic quasi-particles. So to appreciate the significance of this dispersion, it's useful to go back and remind ourselves how do free electrons behave. So free electrons in vacuum are described by this relativistic dispersion relation, where at very high momenta, it's linear. And then at low momenta, the mass becomes important. And we have this, this gap that we can view as a mass gap. And we know from particle physics that we can understand free electrons as massive Dirac fermions, which obey the Dirac equation, and as well as this relativistic dispersion relation. So in this material, when we performed the systematic ARPA's measurements and we sort of mapped out the electronic structure, we came to the conclusion that it looked something like this. And so now we have a linear dispersion, but it's massless. We lost the electron mass, and so this is sort of a fascinating fascinating part of studying topological phases, that we have these exotic emergent quasi-particles which are very different from free electrons in vacuum. And so in this particular case, this is a real material that we have where crystals, but we know that it hosts massless Dirac fermions. And so it's useful to keep track of the degeneracy of the bands. So here, every state in these bands is doubly degenerate. This is not so different from the free electron case. So we have a spin-up, spin-down degeneracy. You can kind of understand it in a similar way for cadmium arsenide. And it's sort of related to the fact that this material is non-magnetic. So spin-up and spin-down is kind of the same. But then these touching points between the bands, which are sort of giving rise to these massless Dirac fermions, these are fourfold degenerate touching points. We have two bands, doubly degenerate, that are meeting at a point. And this high degeneracy requires some symmetry to be present in the system. So in the case of this material, it's a C4 rotation symmetry. So we have a few concepts that are kind of closely linked. We have topology, which is closely related to massless quasi-particles in the bulk, such as these massless Dirac fermions. These are closely related to band degeneracies. So the fact that these two bands are pinned together at a point gives you this massless quasi-particle. And then the band degeneracy itself is closely related to symmetries of the system. So in this case, the rotation symmetry. Okay, so in this example, we found a material where we can remove the effective mass of the electron. We can actually do things that are even more exotic. So here's here again, let's view this cone as a Dirac cone. So doubly degenerate bands and then fourfold degenerate touching points. And we can actually separate these two copies in momentum space. And then we end up with two massless quasi-particles, which are generically singly degenerate everywhere with a doubly degenerate crossing points. And the equation of motion for these excitations is now the Weyl equation. And so we can view these as Weyl fermions. And so again, we can find real materials in nature that exhibit these quasi-particles. You can directly capture their energy dispersion using ARPAs. So the first material is tantalum arsenide, and here's ARPA's spectrum, where we can directly see the linear cone dispersions of the Weyl fermions. And this example is particularly exciting because it's not just about changing the mass of the Dirac fermion, we're actually creating a new particle. And it's also is exciting because this particle has been known in the sort of high energy theory context since 1929, has not been observed as a fundamental particle in nature, but it turns out that it arises in topological quantum matter as an electronic quasi-particle. This phase also is a great context to understand the bulk boundary correspondence. So we have these exotic bulk quasi-particles, and then we have a topological invariant, which is the Chern number, but I won't talk too much about that here. And then on the surface, we have Fermi arc surface states, which are connecting the Weyl points. And by tuning the parameters of our ARPA's measurements, we can go from a bulk sensitive regime where we're mostly sensitive to the Weyl points to a surface state sensitive regime where we can see the Fermi arcs. And then we can directly observe that we have these two arc features which are connecting the Weyl points. And well, maybe briefly for later, let me also introduce you to this notion of a loop cut, which I'll use later. So in order to kind of directly check that we have Fermi arcs, one thing we can do is so you have this Fermi surface map, which is sort of Kx, Ky, and then binding energy, which is going out of the plane. We can take this cylindrical slice of the data, and then we can kind of unfurl that cylinder and get a two-dimensional image where we have a momentum that's running along this circle, and then binding energy, which is here the out-of-plane direction on this three-dimensional data set. And then we can directly measure the Fermi arcs, which on this cut take the form of chiral edge states. And so this provides a direct measurement of the Chern number, and this is sort of the strongest direct experimental evidence that we have this exotic. We have these exotic topological surface states, which then also, by the bulk boundary correspondence, sort of independently confirm the Weyl points in the bulk. Yeah. Any questions? Okay, so while massless Dirac fermions, Weyl fermions, so these are still sort of very much in the spirit of traditional particle physics. But the landscape of emergent quasi-particles and condensed matter is really vast, and so we can even go further. We can go far beyond what's sort of known or expected or proposed in particle physics. And so the Weyl loop is an example of such an exotic particle. So let's first try to understand its dispersion. So we can start with this cone. Let's take this as a Weyl point, so singly degenerate with a doubly degenerate crossing point. We can, if we have some symmetry in the system, such as a mirror symmetry, we can actually sort of go from a Weyl point to a Weyl loop. So whereas a Weyl point has a twofold degeneracy at a point, a Weyl loop will have a twofold degeneracy on an entire closed curve in the momentum space mirror plane. So it's like some kind of series of two-dimensional cones that are all sort of assembled together to form this loop structure. So a useful way to sort of understand this further is you start with, well, so your crystal has some mirror symmetry. So you have, a real space mirror plane. And then you go to momentum space. And now we can look at our bulk Brillouin zone. And then we have the momentum space mirror plane, which in this diagram is kx equal to 0. And so then we sort of pull out this mirror plane slice from the Brillouin zone, and we sort of examine the electronic structure on that slice. So then the axes are ky, kz, and then the binding energy. And so that's sort of what this cartoon is trying to show, that we've sort of pulled out this slice from the mirror plane, and then this is what the electronic structure looks like. So a Weyl loop is a type of line node. So Weyl refers to this, the degeneracy, so the degree of degeneracy, so the fact that it's twofold, so it's similar to a Weyl point. And then you can also, of course, have Dirac loops, which are, fourfold degeneracy touching points on a loop, which is the analog of Dirac points, or massless Dirac fermions. And in this picture, I'm ignoring spin-orbit coupling, but I'll come back to this later. Okay. So now let me start presenting our data on the first compound, CO2 MnGa. So here's the crystal structure. It's a full Heusler crystal. You can already see it's very symmetric. It has plenty of mirror planes, for instance, and so this is already sort of pointing to the Weyl loop. This is, we have we have the right symmetries in this crystal structure to have the Weyl loop. When we started studying this material by ARPAs, we started seeing a lot of spectra that looked like this. So this is at a fixed photon energy, which is like some fixed kz. And then we're slicing with a fixed ky. And we're looking at the spectrum as a function of kx and binding energy. And note that the mirror plane, just as in the example I showed earlier, the mirror plane corresponds to kx equals 0. So it looks like we have some kind of band crossing, which is sitting at kx equals 0, sitting on the mirror plane. So when we first started seeing these results, we said, okay, well, maybe this is a point touching of two bands. So then what do we expect from our data if that's the case? If we sort of change ky and we step through this cone step by step, then we should have a special ky where we see a two-dimensional cone. And then if we step away from the special ky, we should have some kind of conic section, some hyperbola or something, which reflects the fact that we have just a point touching. So we acquired this data set, and we found something like this. So in fact, we saw that the cone appears to persist in a range of ky. There's no special ky, and it doesn't appear to gap out as we shift ky. So then we said, okay, well, maybe we're looking at a structure like this, where we have two bands that are intersecting along a line. And then when we slice in ky, we're sort of chopping this object at various locations, but we always get this cone dispersion. And so then we sort of threw away the point touching picture. And then we said, okay, well, what else do we know about this material? Well, we know it's ferromagnetic. The magnetic moments of the manganese and the cobalt have been measured by neutron scattering experiments. We also performed our own magnetization measurements of our samples. We found a Curie temperature of 690 Kelvin. And these ARPAS measurements are done at about 20 Kelvin, so far, far below the Curie temperature. And then we know in ferromagnetic materials, okay, it's sort of spin polarized, time reversal symmetry is broken. So we have generically singly degenerate bands, which are all spin up or have one spin state. And so then we said, okay, well, maybe we have two bands which are singly degenerate, and then where they cross, that's a twofold degeneracy. So then this sort of took us in the direction of a Weyl loop understanding of this material. So we can also look at this data from another point of view. So here it's cutting in KY. So now let's imagine we have sort of the same data set, but we're cutting, let's cut down energy. So this is now plots which are KY versus KX, the electronic structure, still fixed KZ. And now we're stepping through in binding energy. So starting at the Fermi level, stepping down deeper and deeper binding energy. And what we observe is this kind of bracket shape, which then turns into a point, which then turns into another bracket that's kind of opening in the other direction. And so is this consistent with our Weyl loop, sort of tentative Weyl loop picture? And after some thinking and drawing some cartoons, we found that actually it is consistent. Here's a simple cartoon where now I've emphasized that we're cutting with the constant energy slices. We've got, if we're above the Weyl loop, then we're just cutting entirely in the conduction band, and then we get this constant energy contour, which is opening to the right. As we sweep down in energy, we start to pick up the Weyl loop. We intersect the Weyl loop at a point. And then as we continue to move down, eventually we go through the Weyl loop entirely, and then we're completely in the valence band, and then we get another bracket constant energy contour opening to the left. And you can see sort of this is a slightly fancier version of this cartoon where you sort of imagine that, okay, as you sweep down in energy, you just have an electron pocket from the conduction band, and then as you sweep down, you sort of have this point that moves from left to right and kind of zips away the electron pocket and unzips a whole pocket. And so these constant energy cuts in our photo emission data are consistent with this picture. So then the next step, we said, okay, well, can we understand this theoretically? So we did a first principles calculation, ignoring spin-orbit coupling in the ferromagnetic phase, which corresponds to these cone cuts that I showed earlier. And we found we saw a cone. We could verify that it was gapless in a DFT, verify the band degeneracy, and and indeed we have this Weyl loop in first principles calculation that matches with our ARPA's results. So we explore this material further in theory. We decided to map out all of the Weyl loops throughout the entire Brouillard zone to sort of get an overview, understanding what's going on kind of near the Fermi level in this material throughout the Brouillard zone. And so here's what we found. So it's rather complicated. There's a lot going on here. So the first thing I think to understand this picture is, looking back at the crystal structure, we have many mirror planes, and we also have cubic symmetry. So basically, if we have one mirror plane which has a Weyl loop, then by cubic symmetry, it's going to be copied several times in the Brouillard zone. So we sort of recognize these copies. So for instance, there's this small red loop, which has these 3 copies. And we said, okay, so these are distinct families of Weyl loops that are symmetry related. We've pinpointed 3 families, red, yellow, and blue. And so, this is sort of naturally related to the symmetries of the system. So then we wanted to go back to our data and see, okay, can we understand our data more deeply now that we have this systematic calculation? So to do that, it turns out it's useful to project this upward. So the surface that we're studying is this top face of the cube. So we project the momentum space upward, then you get a picture that looks like this. You have all these Weyl loops that are pushed up, and so this is the sort of projected Weyl loop structure. And then when we went back and we compared this with our photo emission results. So then we realized that this bracket shape that we analyzed earlier, we could match this back up with the blue Weyl loop. And we also saw near the center of the square feature, which is matches pretty well, or it seems to correspond to the red Weyl loop. And then around the border, we have this kind of buckled square shape, which traces out the buckled square shape of the yellow Weyl loops in calculation. And so we're able to see signatures of all three families of the Weyl loops in our photoemission spectrum. And so the combination of this sort of direct experimental verification, the theoretical confirmation, and then matching up the theory and experiment closely, this sort of all provides evidence supporting the Weyl loops in CO2 MNGA. Are there any questions?
Yeah, I'm wondering, all you're showing looks like it is a pure bulk effect. So there are no surface effects are involved so far, right? Is it correct?
That's right. So for the moment, I haven't talked about surface states. I will shortly, but it is true that this material mostly bulk. Yeah, thank you. Thanks for the question. Anything else? Okay, so let's review before I go on. So what are the key ingredients? So it's pretty simple. We need mirror symmetry, which is very common. Many materials have mirror symmetry, and we need ferromagnetism, also kind of very common. So we should expect to find this structure in many materials, the Weyl loop structure. And in fact, that's kind of what happened. Shortly after, while we were sort of finishing up this work, we started exploring this material, CO3 SN2S2, and we realized that we have the similar situation. Here's the primitive cell, and you can already see that it's mirror symmetric, and it's ferromagnetic with a transition temperature of about 175 Kelvin. So again, we have these two very simple ingredients, and so reasonable to ask if there are Weyl loops in this material. So we explored this by ARPAs, and we tried to focus on, so here's the mirror plane in the bulk Brouwer zone. This is exactly the same image as from a few slides ago. And we focused on EK cuts in ARPAs which are poking through the mirror plane. So it's also the same cuts as what I was presenting with CO2 MNGA. So here's an example of what we saw. So we started at 125 electron volts. This is the energy of the incident light. And like I said, this relates closely to KZ. So this is some fixed KZ. And then there's also some fixed KY, which I haven't written down here, but there's some fixed KY. And then, so then the mirror plane corresponds to 0. Kx equals 0. And so then we have the spectrum Kx as a function of binding energy, which on this plot corresponds to this dotted line, poking through the mirror plane. We then acquired a Fermi surface at the same photon energy that looks like this. So here now we're exploring in KY, still the same photon energy, so it's the same KZ, but now the binding energy is the Fermi level, so it corresponds to this dotted line. And then the location of this cut on this Fermi surface is this dotted line. And so we see a cone with a point-like Fermi surface. So again, the natural thing to ask is, do we have some cone, some point touching in this electronic structure? And so to investigate this, one important step is to change the photon energy to sort of explore this third momentum space direction. And so here's an example of what we saw. We changed from 125 to 130 to 135 electron volts. And so this is 3 different kind of nearby but distinct KZ values. And then we acquired Fermi surfaces, and we saw that actually at all the photon energies, we have a point-like Fermi surface. And so now this is pointing away from, this is suggesting it's not a Weyl point structure, but again, suggesting a Weyl loop structure. We have like a series of cones that are extended along KZ, and then we kind of can think of these being assembled together to form a Weyl loop. So with these results, we decided to do a more systematic study. We took a lot of data at different photon energies. So here's sort of our complete data set. we have 9 cuts with 9 different photon energies, and also different ky values. So basically, wherever we saw a cone, that's where we fixed ky. So this is sort of purely from an experimental point of view, just looking for cones in your data. And then we to get a clear understanding of these results, we wanted to assemble them all together sort of in one plot. And so that gave rise to this image that you see here. So so this is the mirror plane. So this is this slice with kx equals 0, and then as a function of ky and kz. And now each picture here, for example, this 135 eV, we have this crossing, apparent crossing at kx equals 0. It's at some kz, so it's at some photon energy. We can convert that to kz, and then it's also at some ky. So then we plot that point with the kz that we calculate, the ky that we observe. And then we do that for all these cuts, and we get these 9 points. And so we see that they kind of appear to be clustered around the L point of the bulk Brillouin zone. And we then did this kind of very simple, like low order Fourier decomposition kind of fit in order to that we found could describe all of these points. And so this now is an experimental determination of the full Weyl loop trajectory based purely on our photo emission results. And so this is the first time that, as far as I'm aware, it's the first time that the Weyl loop trajectory has been mapped out, completely from ARPAs. Okay, so yeah, so this is a sort of a natural point to summarize the results so far. So 2 magnetic materials, both ferromagnetic, both have mirror symmetry. We observe signatures of Weyl loops from ARPAs in both of them. And in the second material, we are even able to fully map out the Weyl loop trajectory in momentum space based only on our experimental data and sort of, just some symmetry arguments. Yeah. So yeah, so any questions here? Okay.
Did I ask you? So,
yeah, please.
Are any spin splitting effects are seen in these pictures? I cannot recognize it.
Yes, so spin splitting is seen everywhere in these pictures. So for example, this material is a half metal. So all the bands near the Fermi level are spin up. And then we don't see bands that are spin down. That's not something that we can say from the data, but that's based on first principles calculation.
Okay.
Yeah, and the same is true in this material. So actually, in this calculation, I didn't stress this, but I mean we know from this calculation that these are all spin up states. Yeah, so these are same spin bands which are crossing. Okay. Any more questions? Okay, so so now let me address the surface states. Going back to the bulk boundary correspondence, the promise was that you have something in the bulk and something on the surface. So I've told you a lot about the bulk. Everything so far has been about the bulk. So it's reasonable to ask, do you see the topological surface states? The topological invariant for the Weyl loop is a Berry phase. It's associated with a pi Berry phase. And the surface state that's associated is the drumhead surface state. So the Weyl loop is kind of like, it's like a ring. And then in the surface Brillouin zone, you have this set of surface states, which is kind of stretched over the ring. So that's why we call it a drumhead. And it turns out that for this, to see these states, it was useful for us to rotate our sample by 45 degrees. So we're studying energy momentum spectra that are along this green line. And so we we acquired some data at 45 eV photon energy at about this position, and we saw that we had 3 cone-like features, which were connected by an additional pair of states that extend from the center cone to the outer cones. So by comparing with first principles, we said, okay, well, maybe these 3 cone-like features are from the yellow Weyl loops. And then naturally, these would be candidate drumhead surface states. So we acquired some more systematic data at different, just varying the photon energy. So the same cut, but varying the photon energy. And this helps us, this changes the kind of distribution of spectral weight. So at certain photon energies, the cones are more pronounced. At others, the extra states, the candidate drumhead surface states are more pronounced. And so, for example, here at 50 eV, we see that these extra states are kind of weak, but then this cone feature is clear. So, okay, so you know, what can we do to kind of understand this further? Well, okay, so first we sort of tentatively assigned the states. We said, okay, maybe these are drumhead surface states, and then here maybe these are the yellow Weyl loops. Then we said, okay, well, we need to check that this is a surface state. So we studied this line cut. So now this is a one-dimensional data set, fixed kx, ky, kz, just varying the binding energy. And this is sort of a standard ARPAS technique to check that you have a surface state. If it's a surface state, then it should have no kz dispersion. And so then it should be photon energy independent. So the location of this peak should not change as we vary the photon energy. So we performed that experiment, and this is what we saw. So this 45 eV line cut corresponds to this trace. And so this peak corresponds to the state of interest. And then we varied the photon energy and pulled out all of the all of the corresponding line cuts from all the photon energies. And we see that, indeed we have a peak, which is visible for all these photon energies, which doesn't shift in binding energy. And so this suggests that it's a surface state. Then, of course, we can also compare with calculation. So this is the analogous DFT result. And we see here, we've got these 2 extra drumhead states that are connecting the center cone to the neighboring cones. And so this combination of the systematic ARPAS results, photon energy dependence, and DFT, this is all suggesting that these states are drumhead surface states. Oh, I see it says Ganendra raised hand. Does that mean you have a question?
Yeah.
Yeah,
So,
go ahead.
In reference to your PRL paper in 2017, you have made like 4 checkpoints to find the formula, right?
Right.
Can you make such a checkpoint for this drumhead surface in this kind of material?
Yeah, that's a very good question. Right now I can't. I'm not sure. I think it's the best thing is that you would want to just see that it connects the Weyl loop everywhere. But it's not clear if you can come up with, or it's not clear what, if there are other ways that you could demonstrate it. And it's not clear what the sort of necessary and sufficient data set is. Yeah, but it is just sort of intuitively that, okay, we expect a drumhead surface state like this, and then we see some state connecting the cones, and it matches in calculation. So kind of at this stage, this is already like, we're very happy to see this. Yeah. Thank you. Any more questions?
I'll ask if I have any.
Sure, thanks. Okay, so that's drumhead surface states in CO2 MNGA. let me now, so I'd like to comment on spin-orbit coupling. So spin-orbit coupling actually messes this up. So if you have spin-orbit coupling, in most cases, you will gap out the Weyl loop. I mean, it doesn't mess it up. I mean, it's still there, but it tends to be gapped. The exception is that if you have the magnetization direction out of the mirror plane, then that mirror symmetry, if that mirror plane is hosting a Weyl loop, it will remain gapless. So in CO2 MNGA, the spin-orbit coupling is very weak. So we sort of know from our experimental data and first principles that it seems to be safe to ignore spin-orbit coupling. To study the effect of spin-orbit coupling, it's reasonable to focus on CO3 SN2S2. So in this material, the spin-orbit coupling is sort of moderate. And also we don't have this mirror plane, perpendicular to the magnetization direction. All the mirror planes are broken by the magnetization when spin-orbit coupling is included. Basically, all these the mirror planes are sort of standing up, and the magnetization is pointing up, and so the mirror symmetry is broken by the magnetization with spin-orbit coupling. So people have performed some DFT in both regimes, with both approximations for CO3 SN2S2. So here's without spin-orbit coupling. You have, this is the calculated Weyl loop. And then with spin-orbit coupling, it gaps out almost everywhere, but it leaves behind 2 Weyl points. And so, here's the view with the full momentum space. You have a few Weyl loops like this, and then that's without spin-orbit coupling. If you include spin-orbit coupling, it gaps out almost everywhere, except at these 2 points, which then become 2 Weyl points, one of each chiral charge. So of course, we after we mapped out the Weyl loop, we said, okay, can we access this spin-orbit coupling physics? So this involves sort of looking inside the Weyl loop close to the crossing point and seeing, can we resolve these gaps, and can we see that we have some Weyl points? And it didn't work. So the problem is that you can see from this systematic data set that we have spectral wave persisting all the way to the Fermi level, basically at every photon energy. And in some cases, like at 120 eV, the top of the band is just cut off by the Fermi level. So at this stage, it's hard to directly experimentally study the spin-orbit coupling gap to see whether or not we have a spin-orbit coupling gap at any particular photon energy or any particular point along the Weyl loop. And so we weren't able to kind of unambiguously show that we have Weyl points using ARPAs. Basically, the SOC is still kind of small, and the bands, or alternatively, the bands are too broad, or the resolution isn't good enough. So then we said, okay, well, so we have the Weyl loop. The Weyl points are kind of hard. We can't really look into the spin-orbit coupling gap. What about the fermi arcs? We have this topological bulk boundary correspondence. We know that if we have Weyl points, we should have Fermi arcs. Even if we can't see the Weyl points directly, maybe we can still show that Weyl points must be there by accessing the Fermi arcs. And so, well, the short version of this story is that it's also inconclusive. And so, but I'd like to share with you kind of our thinking and how we came to that conclusion. So to do this, I need to review a little bit about how, this is actually the paper that Ganendra mentioned. This is how do we show Fermi arcs in ARPAs? And so here's a cartoon where we have a Weyl point at the center of the BZ, one at the corner, and then here's the surface BZ where we have a Fermi arc connecting them. And the recipe, the kind of experimental, direct experimental recipe for showing that you have Fermi arcs is you take some cut through the surface BZ with your surface sensitive ARPAs measurement. And it can be a straight cut. It could also be a loop cut. And then you look at that slice, you count the number of modes that you have propagating in various directions. And if you add them all up and you get a non-zero number, then you know that you have a Fermi arc. So this is exactly this data that I showed in the introduction for tantalum arsenide. We took this loop and we, if you then unfurl the cylinder cut, you see, okay, you have two co-propagating modes. So this gives you a non-zero net number of edge states. And then that means that there must be some Weyl points enclosed in this loop. And so the problem ends up being, as I'll show in the next slide, the problem is that in this material we have too many bulk states, and the bulk states get in the way. So in this data set, there are no irrelevant bulk states that interfere with your edge state counting. And that's sort of the key element, that you need to have these cuts which go through bulk gaps, so there are no bulk states. And this condition we couldn't satisfy with CO3 SN2 S2. So here's our very beautiful state-of-the-art data sensitive to the surface states. So here's the Fermi surface. This is looking at the corner of the BZ, the K-bar point, here's the M-bar point. And we see two sets of surface states. We've got this kind of triangle-like set of surface states, and then we have these additional states here, which are a bit further away. So we can first try to understand this by looking at with calculation. So we go to calculation, we calculate the same region of momentum space, and so in calculation we have the Weyl points are arranged like this. You can see already there's a lot of bulk, and there's a lot of bulk states, and the bulk states are bad for surface states. They kind of swallow up the surface states. There is a Fermi arc here, which it's pretty clear in DFT that it's connecting these two Weyl points of opposite charge, but it's already kind of partially merged with some irrelevant bulk states. And then we also have this trivial surface state, which is just kind of encircling the K-bar point, and doesn't seem to be participating in the topology. So if we wanted to be kind of optimistic, we could just match up. We could say, okay, we have some K-bar state, Fermi arc, Fermi arc, and this agreement does provide some evidence for Weyl points, but the stronger evidence is really in experiment if we can do this. The problem is that of course, especially for magnetic material, the DFT not always correct. So it doesn't always match ARPAs. So you need to what we really want from an ARPA's point of view is to kind of really, from our experimental data alone, provide direct evidence for Fermi arcs. And so it turns out that we can't do that here. You can, if you really just look at the data, you can see, for example, you have this state which looks like it goes into the bulk and then kind of comes out, goes back into the bulk, comes out. And so it's hard to say. This could be just a trivial closed surface state. We could have three surface state pockets. And the Fermi velocities are opposite. So if you just imagine cutting here and then trying to form some kind of loop similar to this, then these guys would always cancel each other out. If you want to avoid one of them, then there's too much bulk. You crash into the bulk states, and then you lose track of your count. So this is sort of our current state-of-the-art understanding for the topological phase in CO3 SN2 S2. We have some indirect evidence for Weyl points and Fermi arcs, but it's not conclusive. So from the ARPA's point of view, I think that the Weyl physics, the Weyl point physics, is not particularly clear, but definitely the Weyl loop is there, and we can, as I said, we can map it out in momentum space. We can study its energy dispersion, Fermi velocity, and sort of, compile an extensive data set on the Weyl loop, which is sort of, supporting the fact that, this is a Weyl loop magnet. Okay, so yeah, any questions? What time is it? Okay, yeah, any questions?
Coming back to last slide, I wanted to just to comment. When you do DFT calculations, you use a slab of given thickness.
Yes.
And you know, if you try to change the thickness of the slab and see what's going on, you can grasp the effect of surface-surface interaction on the slab, opposite surface. They may disturb somehow the results.
Yeah, I don't know about surface to surface. I mean, I know people play a lot of games with the surface potential in the DFT calculations, and you know, that's also part of the problem. That, I mean, not the problem, but you know, if you play with the surface potential, you can usually match the DFT to ARPES. So that's also why it's may not be very meaningful. Yeah, but I don't know about surface to surface.
Okay, I just some of my colleagues did such kind of calculations for other materials, and they see how things are changing when you make slab thicker and thicker. Some significant change may happen.
Right. I see. Yeah. So in this case, this is like a half infinite. I think this is like a half infinite setup.
Thank you.
Okay. So it's already 4. So I had one more topic, but let me just go through this kind of quickly. So there's an interesting connection between the Weyl loops and the anomalous Hall effect in these materials. And this is something that's, you know, very exciting to me, because I think the anomalous Hall effect is very large. So here's a table of many materials, and it's plotting the anomalous Hall effect. Relative to the longitudinal conductivity. So this axis kind of doesn't matter. What people are typically interested in is how to make this effect larger. And it turns out that the anomalous Hall effect in CO2 MNGA is really huge. The only materials that are larger are iron. And so part of our study is we tried to show that that the Weyl loops are actually driving this giant anomalous Hall effect. So we did this analysis where we combined, so this red curve is DFT. This is the calculated intrinsic anomalous Hall. And then we took our experimental ARPES Fermi level, which we found is 80 EV below the nominal Fermi level in DFT. And then we looked at this intersection point, the horizontal line and the red curve. We said, okay, this is what we predict is the intrinsic anomalous Hall response. And then we did transport measurements, and we extracted from a scaling analysis of transport data, which, you know, so I've skipped the details, but we get some transport experimental value for the intrinsic anomalous Hall effect. That's this vertical line. And then we see that we have a good match. So this suggests that the Weyl loops are driving the anomalous Hall effect. We haven't yet had a chance to do a similarly quantitative comparison between ARPES and transport for this material, but it looks like a similar story is playing out. Somebody, you know, other groups have calculated the Berry curvature distribution. You've got Berry curvature hotspots around the Weyl loop, and then the predicted value for the anomalous Hall effect is sort of comparable. It's very large, and it's comparable to the experimental value. So this is again pointing to the Weyl loops driving the anomalous Hall effect. And that's not the only exceptional transport property of these materials. So they also have a very large anomalous Hall angle, which is the ratio of the anomalous Hall effect to longitudinal conductivity. So here again in this plot, many materials, and you can see that CO3, SN2S2, and CO2 MNGA are really outliers, very large anomalous Hall effect and large anomalous Hall angle. They also have a very large anomalous Hall factor. So here again, many materials, but these guys are outliers. And they also have a giant anomalous Nernst effect. So here again, I think CO2 MNGA sets the world record for the anomalous Hall, for the Nernst effect. And CO3 SN2S2 is also very high. And so okay, from an ARPA's point of view, how can we understand this exceptional transport behavior? I think it's kind of natural, because if you've got a point touching, if you have like a Weyl point or Dirac point, you care a lot about the position of the Fermi level. The Fermi level has to be at the point or very close to the point. If you have a Weyl loop, it's dispersing in energy. So your Fermi level can be kind of in many places. You have a range of acceptable Fermi levels. So as long as you're sort of roughly in the ballpark, you will pick up some of the Berry curvature from the Weyl loop, and you'll get a large transport response, anomalous Hall or Nernst response. And so I think in some sense, these materials are kind of shaping up to be the best among all the topological materials we're familiar with so far in terms of generating these giant transport responses. In the case of CO2 MNGA, it's very easy to observe, and it's all the way up to room temperature. So it's just very, very large and robust. And I think a natural next direction is to do some optics experiments that are sensitive to the Berry curvature. So I don't think that's been done yet for either of these materials, and it's kind of the natural next step. Also, you can think, okay, is there any way we can get a quantized response from these materials? So this large anomalous Hall effect, it's large, but it's still not quantized. And then a separate interesting direction is composite loop structures. So for example, people have proposed crazy theoretical models where you have, for example, a Hopf link. You have two Weyl loops that are linking each other in momentum space. You also could imagine chains and knots. And so it's interesting to think about real materials that could exhibit these composite Weyl loop structures. And lastly, there's a whole interplay between magnetism and topology that I haven't really explored. You can imagine changing the magnetization direction, and that might change something about the topology, or looking at different magnetic domains, or looking at domain walls. And so, so I think it's a very interesting topic, and I'm excited to see what kind of new phenomena will be discovered relating to magnetic Weyl loops in the future. Yeah, so thank you very much.
Okay, thank you, Ilya. So now the floor is open for questions. So if you have a question, just unmute and please ask to Ilya.
I'm Ganel again. So since the presence of Fermi arc is not kind of well established in this material, can it be true that it has different type of Fermi arc that we never have seen before?
It's definitely possible. I mean, it's I don't expect any new kind of Fermi arc. I think, okay, maybe the closest thing that comes to mind, I think what's interesting is that it's kind of degenerate with the bulk, but still seems to be there in calculation. And so what would be neat is if we sort of had this kind of persistent Fermi arc, where even though it's surrounded by bulk states, it still survives. And it reminds me of some work on mercury telluride. Chang Liu, who was also in our group a while ago, he saw this Dirac cone in mercury telluride through the bulk states. So I guess that could be a situation here if we keep exploring this data and have higher quality data and so on.
Okay.
Any more questions? Okay, Ilya, I have a question. So what do you expect for optical property for this kind of Weyl loop system, different than Weyl point system?
Good question. So I mean, it's I know that I guess it's not okay. So I know that current Faraday rotation, right? It's also driven by the Berry curvature.
Yeah, yeah.
So you should have, I guess you expect a large, Kerr effect, but I don't know how easy that is to distinguish from. You may expect different contributions to the Kerr rotation, for example, from the magnetization versus from the Berry curvature. So I don't know how easy it is to separate these effects. And then there's also the issue with the type of samples that you're measuring. So I know for some of these optics experiments, people like to measure thin films. So these are available for CO2 MNGA, but they're not available, at least not widely available yet, kind of still under development for CO3 SN2S2. So I think it also depends, on these experimental constraints.
Another technical question. So how easy these two compound for the cleaving?
It's so the Heusler is hard. I mean, yeah, you probably know yourself. So the Heusler compounds are hard to cleave, but it cleaves. Okay, so in the case of that sample, we can create these long bars, which are then easier to cleave, and the cleave success is maybe 50%. So it's pretty easy to work with. CO3 SN2S2 also pretty easy. It's easier to cleave. It's layered, but it behaves rather three-dimensionally. So the layers are kind of close together, and it doesn't cleave completely flat, but it's pretty easy. Yeah, maybe also 50% success, or maybe more in terms of just the cleaving success. Yeah.
So the magnetic domain is large enough for the beamline spot?
Right. Yeah. Good question. So this is another issue that no. So the magnetic domain is smaller, maybe best case comparable to the beam spot. But if you are interested in these non-spin-orbit coupling properties, so we ignore spin-orbit coupling, that means that the band structure is not coupled to the magnetization direction. So then we can average over many domains, and we will see the same bands. The challenge is that if you're interested in looking at the spin-orbit coupling physics, which is like a natural next step, then you will have different copies from all the domains, and then that creates some difficulty.
I see. Any more questions? Okay, if not, let's thank Ilya for your time and wonderful talk. And thank you everybody for participating on this special seminar. Thank you.
Yeah, thanks for coming. Thank you very much. Yeah, thanks for the opportunity.